So, in this last lecture on detailed routing, we shall be looking at some more techniques, means one more technique for channel routing, then we shall be moving to some other very specialized routing techniques. We shall not be going into detail because the algorithms are a bit involved there, and I do not intend to discuss complex algorithms as part of this course. Rather, I shall try to motivate you, try to make you appreciate what the problems are, and with illustrations I shall try to explain how the problems are typically solved. Okay. So, first let us compare the channel routers that we have already seen. So, we have the left edge algorithm, the extension with dog legs, the Oshimura-Ku net merge, and the last one that we discussed, the greedy algorithm. These are all grid based models. Dog legs, the basic LEA does not support dog legs, but the others they support. Vertical constraints, the basic LEA did not support it, but the extended LEA that supports, but others they support. Cyclic constraint, only the greedy algorithm supports. Okay. So, you see, if you have a cyclic constraint in the VCG, you have two alternatives to start with. So, either you can move some of the terminals around if possible, so that you break the vertical constraint, make some edge non-existent. For example, 1 was top of 2, if you can move 2 by 1 position, so that there would be a no connection below 1, that 1 to 2, that edge will go out. So, if possible, if it is possible to move such terminals around, you move them, which means you are moving some cells around in the standard cell layout, if it is allowed. Otherwise, you will have to go for something like greedy algorithm, okay, which can handle dog legs and also the cyclic constraints in the VCG. Okay. Now, we shall briefly talk about 3-layer channel routing without going into much detail. There are of course several approaches which are there, but we shall be looking at one possible approach. There is an extension to the net merge Oshimura-Ku router. There is another approach which starts with a 2-layer solution and extends it to 3-layer solution, and there is a hybrid router which considers horizontal vertical horizontal and also vertical horizontal vertical, combine both of them together and try to complete the 3-layer channel routing. Okay. So, let us try to see. So, the method that we are briefly talking about is the one of getting a 3-layer solution from a 2-layer solution. Conceptually, this approach is similar to the Oshimura-Ku algorithm. So, what we do, we systematically transform a 2-layer solution into a 3-layer solution. You see, let us try to understand. So, what happens in a 3-layer solution? I have 3 metal layers M1, M2 and M3. Now, in 2-layer solution, I have only M1 and M2. I put all horizontal segments on one layer, all vertical segments on the other layer. Now, in the Oshimura-Ku algorithm, net merge algorithm, what we are doing, we were trying to merge 2 or more nets to form a composite net, such that all of them would be laid out on the same row, let us say same horizontal track. But now, when we think of a 3-layer solution, suppose we think of horizontal, vertical, horizontal, HVH model. So, I have 2 layers in which I can run my lines horizontally and 1 layer where I can run the lines vertically. So, now my extended problem becomes something like this, that when I merge 2 nets into a horizontal composite net can be laid out either in layer 1 or layer 1, layer 3 together, one on top of the other, same relative location. So, this layer 1 and 3 both allows horizontal segments to be run. I can consider them as 2 composite nets and I can run them together in the 2 nets, okay, 2 layers. So, the concept is something like this. So, in the conventional net merge algorithm, what we do? We merge the nets such that the merged nets are assigned to a single track on a single layer. But here what we are doing, that such composite nets we are again merging to form a super composite net. Like you see, in Yoshimura-Ku algorithm, when I merge 2 nets, it means that their horizontal constraints do not conflict, their vertical constraints also do not conflict. So, they can be easily put on the same track in the same layer. Now, suppose I have run Yoshimura-Ku algorithm like this. I have several such composite nets. So, in the earlier example that you saw, there were 5 such composite nets. We laid it out on 5 layers. Now, what we look at is among these 5 composite nets, can we merge 2 of them together, remembering that now we have another additional horizontal layer available with us. Do we have 2 composite nets which we can possibly place on this M1 and M3 in the same location, same track position? That will of course reduce our total channel height. Okay? This is what we are looking at. So, we are trying to merge the composite nets to create something called super composite nets. This is an additional step here. So, our objective is to reduce the number of super composite nets. See, super composite nets basically means a set of composite nets which are placed on the same track, but possibly on 2 different layers. So, now our target is to minimize the number of super composite nets, which means minimize the number of tracks. If you can reduce the number of tracks, we reduce the total area of routing, because the height of the channel can be reduced. Okay. So, what I said is that 2 composite nets in a super composite net can be assigned to the same track, but maybe to 2 different layers M1 and M3. So, without going into too much detail here, I am just giving you the overall approach. We use some kind of a track ordering graph, which is means one level of abstraction beyond what was used in the Yoshimura-Ku algorithm. In the basic net merge algorithm, we are using the graph which depicted the vertices that we can merge together to assign to the same track. But now we have another higher level graph representation, where this composite nets we are further merging to create something called super composite nets. Okay. So, now we have a choice, we have M1 and M3. I have 2 super composite nets, let us say M1 and M2, let us say C1 and C2. So, I can put C1 in layer M1 and C2 in M3, or the reverse. So, I have choices, which one to put below, which one to put up. There are 2 layers available now. Okay. So, this graph will reflect that. So, vertices in this track ordering graph will represent the composite nets or tracks. Okay. Okay, I am just showing the example graph without going into some details. This was a channel routing problem which was given, and this was the corresponding track ordering graph, that which track has to be placed before the other. So, I am not going into detail how this was done, but this is fairly straightforward. Okay. So, this track has to be, this is a graph which was created using the Yoshimura-Ku algorithm. This is the graph corresponding to the one which we obtain after merging the nets, as in Yoshimura-Ku 2 layer solution. Okay. So, this graph will tell you how many tracks are required and the dependency, which one has to be on top, T1 has to be on top, then you can have T2, T1 and T2 anyone can be on top, and like this. Okay. Now, you see T1 and T2 can be because they do not have any dependency. Similarly, you see T3, T4 do not have any dependency, either T3 can be above T4 or T4 can be above T3. Now, we have a graph representation like this, that T1 and T2 they are independent, Now, you see this is the solution you get out of the Yoshimura-Ku algorithm. I have not shown the steps. So, you can work out the steps yourself if you want. For this channel routing problem, you will be getting a final track ordering graph like this. Now, this graph says that T1 and T2 does not have any kind of dependency between them, which means you can place T1 on top of T2, T2 on top of T1, or even you can put them on the same track, one above the other, one in M1, one in M3. There is no constraint between them. Similarly, there is no constraint between T3 and T4, but between others there is some constraint. T1 has to be above T3, T1 has to be above T5, T2 has to be above T5, and so on. Okay. So, looking at this scenario from this graph, so what you can do, we can create a scheduling table where you say that we have, okay, this is time, we are using this notional time. Actually, these will indicate the tracks. In the first track, we can place T1 and T2. In the second track, we can place T3 and T4, because now track contains two different layers, M1 and M3. Okay. I can place one of them in M1, one in M3, and T5 remains. Now, I can have a graph representation like this, which tells you that I can put T1 in M3, T2 in M1, or the other, T2 in M3, T1 in above. Similarly, the next stage between T3 and T4, I can place either T3 above T4 or T4 above T3, and last one T5, this T5 I can put either in the M3 layer or in the M2 layer. So, you have so many alternatives, and the edges will indicate the corresponding cost. So, given this graph, you try to find out a path which gives you the lowest cost. Like here, the lowest cost will be this, T1 on top of T2, T4 on top of T1, T3, and then T5 in the lower layer. So, this will be your final solution. So, T1 will be laying on M3, T2 on M1, then T4 on M3, T3 on M1, then T5 on M1. This will be your final solution in 3 layers. So, this is just the basic idea behind how you are extending the output of the Yoshimura-Ku algorithm to extend it to the HVH 3 layer model. Okay. So, the basic idea is like this. Okay. So, we briefly have a look at switchbox routing. We shall not go into the detail of any algorithm because of two reasons. Number one, no systematic algorithms exist. Most of the algorithms that have been proposed and are used for switchbox routing, they are based on some rules and some heuristics which are not very interesting to discuss or teach. So, when you want, you can just refer to them from standard textbooks, and there are a lot of materials available. You can see the various approaches. Switchbox routing, you recall, is a subproblem where the pins are located on all 4 boundaries of a rectangular region. It is an extension of the channel routing problem. Okay. So, terminals exist on all 4 sides. Now, in a channel routing problem, there are so many good algorithms available. Your objective is to minimize the channel height, but in switchbox, you see, the constraint is different. You have pins coming from all 4 sides, which means that it is not easy to compress the size of the switchbox. Maybe there are blocks already placed on all 4 sides. Switchboxes shall not appear in standard cell based layout, there we have only channels, but for full custom based design style, switchboxes may appear. But once they appear, the blocks on the 4 sides are often fixed, you cannot move them around. So, your objective is not to reduce the area, but to ensure 100% completion of routing. This is the main objective, okay, is to ensure that all the nets are routed. So, there are many algorithms which have been proposed. One may be a greedy router based on a set of simple rules, repeat and reroute, that means you proceed with the routing. So, once you get stuck, go back, remove some of the nets which have already been laid out, again retry. And there was another interesting approach that was based on computational geometry, some algorithms there. It is called Beaver. Beaver is quite popular in that sense. Okay? And I am just showing you an example. This is an example switchbox. I mean, you can appreciate the complexity of the problem. There are pins coming from all four sides and you have to interconnect them. Now, that constraint remains that horizontal and vertical lines may be on two different tracks. This is a two layer solution which is shown. So, horizontal connections may be on layer M1, vertical connections on layer M2, and you can have multi-terminal nets as well. Okay. So, this is the final solution for an example switchbox. So, I shall not go into the detail of any algorithm there. Okay. Okay. So, to summarize this detailed routing algorithm, so you can have either channels or switchboxes. The routing models are typically grid based. You assign layers to the different net segments of a given net. So, your main objective is to minimize the height of a channel, sometimes length of the nets, so as to minimize the delay, and also as I said that the via connections are expensive. So, whenever you make a via connection, it means that you are putting some kind of a drill means inside the fabrication process, and you use a metal to connect one layer to the other. So, once you do this, you can have additional resistive and capacitive effects. Okay. So, less the number of vias, the better. That is one criteria. And of course, switchbox routing, as I said, the objective is mainly to determine routability, not to minimize. Okay. Now, we shall look at a new kind of routing called over the cell routing. Now, this over the cell routing appears only for standard cell kind of a layout. Let us try to understand the motivation behind this over the cell routing and some of the basic algorithm or some algorithmic steps which you can follow for this. The idea is as follows. The idea is that the area outside the channel, you are trying to use them in the interconnection, because the additional layers are not used to that extent. That means, what I mean to say is that in a standard cell kind of a layout, you have the rows and you have the channel. This is your channel. Okay. Suppose in a 3-layer channel routing, if I say a 3-layer channel routing, so inside the channel you are using, let us say, HVH model. So, there are 3 metal layers, you are laying out wires on these 3 layers inside this channel only. But what about on top of these regions? So, here the actual devices are fabricated, the transistors, the gates. So, on top of it, maybe one of the metal layer is available to you, that is free. So, why not some of the connections, like for example, I want to connect this point to this point, instead of going through the channel, why not directly connect like this? Similarly, if I have a way of connecting them, so why not say, for example, I want to connect this point to this point, I find that there is a free space here, there is a free space here. So, what I can, instead of going through the channel here, this region may be quite congested. So, what I can do, I can take it out here, from here I can make a connection here, and from this free space I can again bring it here. So, a part of the net I can lay out on top of the cells. That is why this is called so called over the cell routing. Okay. So, let us see. So, there are several algorithms which have been proposed for OTC or over the cell routing. So, I am suggesting the basic steps in one such approach. In the first step, you are doing some kind of net decomposition, which means if you have multi-terminal net, you partition them into a set of 2 terminal nets. So, again it is like the left edge algorithm, based on the x coordinates of the leftmost terminal, you partition them like 2a, 2a, 2b, 2b, 2c, 2c, like that. Then the nets you classify as one of 3 different types. So, I shall be illustrating this one by one. Type 1 says there is a vacant terminal directly opposite to one of the terminals of the net. This means something like this. So, again I am illustrating. Suppose I have a channel between standard cells like this. Suppose I have a scenario where I have a pin here which is marked as 1, just right opposite there is a pin marked as 0, which means this is not currently assigned. So, if I want, I can take a connection on top of it and do over cell routing here, okay? Because maybe this part of the channel is very congested, I cannot take it here, but I can possibly take it above here, bring it here, then again bring down here. So, this is the so called type 1, which says that there is a vacant terminal directly opposite to one of the terminals of the net. Type 2 says there is a vacant terminal between the 2 terminals of the net. Let us take another example. So, it can be 2 types, either there is a 2, there is a 2 here with a 0 in between, or there can be a 3 here, there can be a 3 on the other side with a 0 in between. These are examples of type 2. Type 2 says that there is a vacant terminal between the 2 terminals of the net, and type 3 means if none of these exist. So, for type 1 and type 2 you can carry out some kind of over the cell routing if you want. This is the basic idea. And step 3 is vacant terminal assignment. Vacant terminals are assigned to each net depending on its type and weight. And how you define the weight? It can be defined as the improvement in channel congestion that can be achieved if you do over the cell routing for this net. So, there are many ways to make an estimate of this improvement in congestion. Like what I mean to say here is that vacant terminals are assigned to each net means like here. So, when you want to let us say this assign this 3 to 3, you can assign this vacant terminal 0 if the net out here is congested. So, what you do? You do over the cell routing from here to here, and from here you move out, and here you can connect it here. Okay. So, you are avoiding the congested region, you are moving it out, taking a vacant cell, taking out from there, and from there you can do another over the cell routing. And one thing is there, during over the cell routing you are not switching from one layer to the other. The entire net, both horizontal and vertical, they are laid out on the same metal layer. This is one difference, because in the over the cell routing you are not allowed to use the via connections, you are doing it on the same metal layer, right. So, after you do this, step 4 says now you are doing the over the cell routing. So, after you have identified the vacant terminals, and in the last step you select which net segments can be routed in the channel and which net segments can be routed over the cell. Okay. So, once you make or take this decision, then you have an idea that which one will move to within the channel and which one will be moving, means not within the channel, but outside the channel. So, let us take an example to illustrate. This is an example channel. So, let us say this is a typical snapshot of the standard cell design style. So, here I have shown 4 cells which are placed, here also there are 6 cells which are placed, and this connection I am showing in between, this may represent a feed through cell, but I am just showing it like this without showing it in a rectangle, closed rectangle. So, this allows a vertical connection to go through it. Okay. Suppose this is one solution. So, here you can see which nets are connected to which nets. Okay. So, this solution was obtained by a greedy channel router. So, you can see that how many tracks you require, 1, 2, 3, 4. There are 4 tracks you require, but of course, this has to be there is a mistake here, this will be a brown connection. Okay. The horizontal one will be brown, not blue. Now, this same problem if you do the over the cell routing, so the possible final solution will look like this. So, the over the cell connections I am showing in red. You see, this pin was supposed to be connected to this pin. This is a type 1 problem, there is a vacant pin just opposite to it. So, you use it just with a vertical segment, you connect to the pin right opposite to it, and from there you do a over the cell connection to connect to this pin. So, you are avoiding this horizontal segment. Similarly, you can see this connection was there, but here this is also type 1, you have a vacant terminal opposite. So, you again do the same thing, move right, connect it. So, in this way you do it. Similarly, you can take some example where it is a type 2, let us say this pin was connected to this pin and this pin are connected. Okay. And type 2 means there is some vacant blank terminals in between. So, what you do, instead of starting from here and going like this, you do a over the cell routing here, come here, over the cell routing here, come here. You will find that this reduces congestion in the net, in the sense that you can take a straight segment and connect to it. Okay. So, in this way you identify the all type 1 and type 2 connection, but again do not blindly use OTC routing for type 1 and type 2 all of them. You use them only if it reduces the channel congestion with respect to some cost metric. So, once you do this, you will get a final solution like this. So, you see, instead of 4 tracks you require only 2 tracks in the channel, which means the rows can be brought very close to each other. Okay. So, the other connections are carried out over the channel, over the cell. Now, in general, in fabrication technologies where more than 3 layers are also available, multiple metal layers are available, you can possibly do the entire routing on top of the cell itself. So, there is a concept which is called channel-less routing. So, all the interconnections are carried out on top of the cells. So, you do not need any area for the channel basically. So, but here I am not discussing that. So, here we talked about the basic idea behind over the cell routing, how it works and how it helps in reducing the number of tracks in the channel. But one thing I am repeating, greedy channel routing, although it appears to be very simple, but it is still considered to be a very powerful tool, because it can handle problem instances where there are cycles in the vertical constraint graph. Okay. So, with this we come to the end of this lecture series on routing. So, in our next lecture we shall be starting with some other very important problems of timing and clocking. In fact, we shall be using several weeks to discuss issues related to this, and I shall be trying to go slow there with a lot of examples and illustrations, because clocking, timing, noise, crosstalk, these are issues which are very important in modern day high performance system design, and we shall be starting this from our next lecture onwards. Thank you.